Moving on with our discussion of heat and heat transfer, we're going to continue with the laws of thermodynamics, specifically discussing the second law of thermodynamics and how this relates to such things as heat engines and heat flow. So although we've seen this example before, we're going to see it again. It's good to keep this in mind as to which way energy flows. So remember, our red hot piece of iron thrown into a bucket of cool water will cause the internal energy of the iron to flow into the water. So heat in these cases flows down a gradient. It flows from hot to cold. And of course, this is the same as putting your coffee in a cold room. The coffee will eventually cool down and equilibrate with the room. I realize that seems like a common sense thing to think about, but of course, we've seen this before and we want to keep this in mind and make sure that something you wouldn't say in words, you don't say in physics terms, and we don't actually violate this particular law. So in terms of reactions that can take place, some reactions are considered reversible, some are irreversible. So such a thing as freezing water and then subsequently melting it back into liquid state. This is a reversible reaction. We can take our water in its solid form as ice, we can melt it into liquid, we can then reduce the temperature and regain our solid ice state. This is a reversible reaction. Examples of an irreversible reaction are such things as chemical reactions. So take CH4, methane, and O2, oxygen, and then combine those together and get CO2 and H2O, carbon dioxide and water. On the surface, it might seem that you could put H2O and CO2 together and then regain CH4 and O2. This, however, is an irreversible reaction. The energies and bonding required to take these two, CO2 and H2O, and get the original reactants back are quite complicated. So you'd have to catalyze this reaction and go through a chain of reactions to come back and get CH4 and O2. You cannot simply put these two together, rearrange them, and get these two back. This is an example of an irreversible reaction. You can do this, but it requires a completely different path. So whenever a system is in equilibrium, such as our water situation, a reaction is considered reversible to the reactants or the products. So we can freeze water and then we can melt it and get ice back. We can vaporize water and we can reduce the temperature and get our liquid water back. In a spontaneous process, the process is considered irreversible. The reverse of a spontaneous process, of course, is called non-spontaneity or not a spontaneous process. An example of this is taking eggs and scrambling them. This might sound a little bit ridiculous on the surface, but it is a good example. If you take an egg in its intact state and then scramble it, you've increased the chaotic state of that egg. You cannot unscramble that egg and reform it and get a nice complete yolk once again. It just won't work. You've increased the entropy of that egg to the point where it cannot be reformed. And these are really all statements that fit within the second law of thermodynamics, or at least pertain to it. And the second law of thermodynamics really states that the entropy of the universe is always increasing in a spontaneous process and remains unchanged in an equilibrium process. Really, what the second law of thermodynamics tells us is which processes in the universe can occur and which cannot. And we can look at this on a variety of levels. We will eventually take it down to the level of just looking at thermal cycles. But right now, there's bigger pictures to look at. So in terms of entropy, what is it? Entropy is a measure of randomness or a measure of disorder. If you increase disorder or increase randomness, you increase the entropy of your system. So the entropy of any isolated system will always increase over time and approach some maximum value. If you leave a system alone and do not maintain it, it will tend towards a state of greater and greater chaos, less and less order. For instance, you could look at this on the macroscopic scale. What happens if you have a building and don't maintain it and just leave it to its own devices? Eventually, weather and decay will cause it to fall apart. Its chaos will increase. Its entropy will increase. So the entropy of a thermally isolated system should never increase. Now, if we mean thermally isolated system, what we're talking about here, this is not contravening the previous statement, we're talking about a situation such as a calorimeter, where there's no exchange of energy with the exterior system. We're just talking about taking water inside there and adding metal and then leaving it completely isolated. The entropy of that system should not decrease because there's a set amount of energy that is exchanged. A larger statement of this is that the entropy of the universe is always increasing in a spontaneous process and remains unchanged in an equilibrium process. So it really is a statement of conservation of entropy. If we assume our whole universe is an isolated system, the entropy of our whole universe cannot decrease, it's always increasing. And there's a couple of important consequences to this that we will come to. But when we're talking about the universe, here is the beginning of the universe. Energy was released at the beginning of the universe in a radiative sense. And what's actually happened since is energy has reordered itself and become far less chaotic and reach a state of lower entropy, essentially. And we've got matter. But energy is constantly being exchanged, and what's happening is the entropy of the universe overall everywhere will increase, and the entropy of the universe is indeed increasing, and what's happening is the radiative energy and gravitational energy that we see in the universe today is being converted to other forms, possibly things like dark energy. And what will happen is eventually we will end up with a dark and desolate universe where all of the energy that we depend on, gravitational, radiative, all of this, has been turned into a form which is unusable to us. But we're talking billions of years in the future, and we're not necessarily worried about this. Something to think about when you're lying awake at bed at night. So, let's get down to thermodynamics. What does the second law of thermodynamics really say for us in terms of heat and heat transfer? It means that heat cannot pass from a colder to a hotter body. We looked at that with the iron. If we drop our piece of hot iron in the water, the energy flows from the hot iron to the cold water. It would not flow from the cold water to the hot iron. It's impossible for any device that can operate on a cycle to receive heat from a single reservoir, that means a supply of heat, and produce a net amount of work. That means you can't get work from nothing. Heat must flow from hot to cold, and then you extract work from that process. So we can only get useful work out of heat if it's transferred from a hot to cold reservoir. So really, what the second law of thermodynamics is saying is which processes occur and which do not. And there's many, many ways of stating it. For us, we're going to say heat flows spontaneously from hot to cold and will not flow spontaneously from cold to hot. We can transfer energy from cold to hot reservoirs, but then we will have to actually put work in to achieve this. And we will discuss that later. But naturally, heat will flow from hot to cold. So there are multiple statements of entropy that you will see in different places. Our formula for entropy, at least one of them, there are two, is that delta S, the change in our entropy, is quite simply put the final entropy value minus the initial entropy value. I'll show you how to calculate S shortly. Other statements, the one we care about, a quantitative measure of the amount of thermal energy not available to do work in a closed thermodynamic system, entropy. What this really states is entropy is kind of an efficiency. It's how much energy is not available for you to extract from your machine. So you have a certain amount of heat, Q, and want to do a certain amount of work, W. But entropy stops you from converting all of Q into W. It's how much energy is unavailable and too chaotic to use. You can also see entropy quoted as a measure of disorder or randomness in a system. In IT terms, it's a measure of the loss of information in the transmitted message. As we've said before, it's also the tendency of all matter and energy in the universe to evolve towards a state of inert uniformity, very cheerful, and, as we're seeing possibly today, inevitable and steady deterioration of a system or society. Entropy, its units are J/K, joules per Kelvin. So the change in entropy of our system is delta S, which is S final minus S initial in joules per Kelvin. And that really depends on only the final and the initial states. It doesn't matter what pathway is taken to go from S initial to S final. It just matters what the initial and final values are. And you do have to pay attention to the sign of delta S. Delta S being negative means your system went towards a more ordered state. So take liquid water and freeze it, you should see a negative delta S. If you have a positive delta S, this means your system went to a less ordered state and became more chaotic. So positive or negative S denotes a more or less ordered state of your system. So as we said before, the second law of thermodynamics actually holds a lot of different things within it, a lot of different conclusions. So the final fate of the universe, this energy going towards some dark, non-radiative form where we will see a dark and flat universe. Ice melting to water, or water being frozen back into the form of solid ice. The degradation of your professor's office over a semester. The Egyptians had this kind of idea, not so much scientifically in the form of entropy, but they actually had two goddesses, Ma'at and Isfet. Isfet being chaos and Ma'at being order, and Ma'at and Isfet were always fighting in the universe as to which one should win, chaos or order, and always coming to a balance. So quite scientific, even though it wasn't really intended. And of course, Little Miss Tidy could become Mr. Messy. So, typical processes that will lead to an increase in our entropy are the melting of a solid, dissolving a solid in a solution, putting such things as sugar or salt into water and dissolving them, taking a solid and making it into a liquid or a gas, just increasing the temperature of a substance, or when a gaseous reaction produces more molecules. If there's no net change in the number of gas molecules, you can have a positive or a negative value depending on what's going on with the system, but it will generally be a smaller change in S. So entropy is our measure of disorder. A solid has a lower entropy than a liquid, which has a lower entropy than a gas. If we think about this in our kinetic form, if we provide heat to this system, we're actually providing more energy per molecule. That means in the solid, these molecules have less energy. As we heat it up, these molecules are receiving more energy and are moving around more, jostling and becoming a more chaotic system. They have more energy in terms of half mv squared to move around. Continue to add energy, and eventually we will turn this system into a gas, where each of the individual particles has an enormous amount of energy and then can fly around at a much higher rate and can bounce off the sides of these walls and one another, and this is a much more chaotic system than the nice ordered solid lattice shown here. So low entropy, high entropy. As we said, entropy always increases in our situation. So how can we account for freezing water? If we place water in a freezer, surely we're just reducing the entropy. And that's kind of true. If we do that and we look just at the water, we reduce the entropy of the water. But as per energy being conserved, entropy must be conserved. So in reducing the entropy of the water, we've increased the entropy of the universe somewhere else. So what that means is if we are going to freeze something, we usually pump some kind of refrigerant through the freezer, and that refrigerant will take energy out of the system and allow you to freeze your water. That means the movement of the compressor plus the evaporation and condensation of that refrigerant plus the warming of the air around the container, because we have to take that warmer energy and dump it somewhere, usually warming the air as the refrigerant lets its energy go, gives us a net increase in the entropy of the universe. So we reduce the entropy of the water at the cost of increasing the entropy of the universe in 3 locations: by the movement of a compressor, the evaporation and condensation of a refrigerant, and the warming of air around the container. So we said essentially delta S was S final minus S initial, which is a relatively simple calculation. So how do we get our S values? Well, our S values actually come from a study of molecular structure and quantum mechanics and allow us to calculate entropy theoretically for most systems. Most substances will use some kind of calorimetric measurements as per the calorimeter at pretty low temperatures to achieve this. So our equation becomes delta S equals Q over T. In most cases I have used the uppercase Q, here it's lowercase, but this does not really matter. So Q here is the heat energy absorbed by the system, T is its overall temperature, and delta S is its entropy. So what it's saying is the entropy is a ratio of how much heat energy is in the system to how much the temperature increases. So there's our equations together. Delta S can be SF minus SI, or delta S equals Q over T. Since Q is heat energy and T is temperature, that means S comes out in J per K, or joules per Kelvin. The entropy of a system really depends on its internal energy and external variables such as volume. And we're coming to another equation that involves the energy of a system and relates that to S. In some thermodynamic limit, that means you can get an equation relating the change in internal energy to the changes in entropy and things such as volume. And that's the fundamental thermodynamic relation. And here it is. If the volume is the only external variable, then the relation becomes this. Delta E, the total energy of the system, is T delta S minus P delta V. T is the temperature, delta S is your change in entropy from here, either formula or both. P is the pressure, and delta V is the change in volume. So we've made a few relations here. Let's take a look at a problem. So we have a 10 kilogram block of water ice and is taken from a refrigerator at 0 Celsius and placed in a warm environment. Several minutes later, exactly 50% of the mass of the ice has melted, becoming water at 0 Celsius. What is the change in entropy of the ice-water system? So we're melting a 10 kilogram block of ice and we're waiting for 50% of the mass to melt. What's the change in entropy? So, first of all, let's find the heat that's required to melt half of the ice. And of course, you should be harkening back to what we discussed in calorimetry and realize this is a melting situation. So Q is equal to mLF. This should have a little f, the heat of fusion. The latent heat of fusion for water is 333,000 joules per kilogram, here given in kilojoules. So Q equals to ml. The mass we care about is when 50% of our 10 kilograms is gone, so this is 10 kilograms over 2, times 333 kilojoules per kilogram. This gives us 1,665 kilojoules. This gives us Q. We're not done yet. We know the temperature of our system is 0 Celsius. This translates to 273 Kelvin. We have 1,665 kilojoules divided by 273 Kelvin. Here I've converted the kilojoules to joules, which gives us 6,098 joules per Kelvin. So that's how you can arrive at delta S, the entropy change for ice moving into water. First find Q, compare that to T, delta S is Q over T. So entropy places constraints on the direction that your heat transfer can go, and also the efficiency of a heat engine. So delta U, in this case, the change in our internal energy of a system, is equal to Q, the total heat available to the system, the total heat energy, minus how much work you can extract. You cannot extract heat from a hot reservoir. You must exhaust it to a cold. So heat must flow from hot to cold, and then you can extract work from it. You can never get 100% of the energy out of this particular situation. You can never have a 100% efficient heat engine. So let's look at the second law, and specifically how this relates to things like heat engines. So when we're talking about a heat engine, we're talking about an engine from which we want to extract useful work. That's the purpose that the engine exists for. So we have some amount of heat energy at what we will call QH, a hot temperature, and we're going to exhaust this to QC, a cold reservoir. Remember, there are no perfect heat engines. You can never get 100% of the energy out of your system. This is actually called the first form of the second law, or the Kelvin-Planck statement, that there are no perfect heat engines. And you often see diagrams like this, showing the direction of energy flow. So let's take a look at this diagram here on the right. Here we have a certain amount of energy, QH, at 600 Kelvin. We're exhausting this energy to a reservoir of 300 Kelvin. So this energy is falling down a gradient of 6 to 300 Kelvin, so a 300 Kelvin gradient. When this occurs, we can extract a certain amount of useful work. We can take some of this energy and divert it to do some work. So we're going from 600 to 300, QH to QC. If we have a 600 Kelvin heat engine that exhausts to 300 Kelvin, this means the engine cannot be more than 50% efficient. We cannot take away more than 50% of the energy in the form of work. We could reduce this to 200. We could change this value and exhaust to ever colder temperatures and increase the efficiency of our system. This system, from 600 to 300 Kelvin, only gets 50% of the work. So this is analogous to, say, creating an engine from a water wheel. In a water wheel, we would have water contained at some height h with an energy given to it by the gravitational potential energy of mass times gravity times height. This body of water would fall and impart this energy in the form of kinetic energy to this water wheel. There would, of course, be loss in the water wheel, which we'll ignore. But if we place our water wheel here, we can only extract 50% of the available gravitational energy. A sensible person would put their water wheel here at the foot of the waterfall, and that would generate much more energy than here halfway up. So any engine that operates in a cycle is referred to as a heat engine. and this engine will return to the same starting point each time its cycle has ended. So this has the same internal energy at the end of its cycle. This means for a complete cycle, the amount of heat energy that is put out should be equal to the work. So a heat engine has to have a temperature difference. If the temperature is equilibrated, then the work done in one part of the cycle equals the work done by this other part of the system. So the net work is zero. We cannot exhaust a 600 Kelvin heat reservoir to a 600 Kelvin heat reservoir. We could go from 600 to 300, 600 even to 550, which would be very inefficient, but we could do it. But if you have an equilibrated system, then no work can be done. So what we mean is something like this. And these equations here for efficiency, we're going to talk about these later on, but they are here just to tell you how much work you can actually get out of the system. So all real heat engines will lose heat to the environment. You cannot extract all of the work from a system. So here's our hot reservoir, and here's Q flowing out. We cannot divert all of this simply to work. We must send a certain amount of energy Q to the cold reservoir and then siphon off what we can in terms of work. The efficiencies here tell you how much work we can take away from this system. So the efficiency here is either work over QH, the Q at the hot reservoir, which is essentially delta Q, QH minus QL over QH, or E is more simplified, 1 minus QL over QH. And using one of these equations really depends on what variable you're given. We'll see these again. So in terms of a heat engine, mechanical energy can only be obtained from the thermal energy in this system. So heat flows down our gradient from high to low, and we extract useful work, W. So those were schematics showing the energy flow in a heat engine system. Of course, the engine itself is a little more complex. You do have to have other moving parts, valves and such, and cylinders expanding and contracting. And of course, in the particular case of a steam engine, you do need to vaporize some water. So here's our boiler where, as per the name boiler, we are applying heat and we are turning water into steam. This causes the steam to move through these pipes, go through this intake valve, cause expansion of this, expand inside the cylinder and push this piston, which then drives whatever wheels or cogs or any other machinery you intend to have connected to it. This exhaust valve will then open during the contraction phase, and the piston will move back down and force out the remaining gases, which will then go back into here. Being water, they will condense back into water, and you can cycle the water back through to the boiler and start all over again. Of course, there will be losses in this system, and the losses we're going to talk about are the losses due to thermal energy. We're not going to worry about the inefficiencies of whatever machinery you hook up to the system, which again will result in a loss of energy. So as we said, engines run on a repeating cycle, and the change in internal energy over one cycle is zero because essentially your engine returns back to its original position. We have a high temperature reservoir which transfers heat, and then we take some of that energy as the heat is exhausted to a lower temperature, a lower energy. We take some of that heat in the form of work. So in dealing with the work done by a gas, we can look at the work done in a mechanic sense. This means the motion of a piston. In a complete cycle for our system, this piston will come down and then return to its original position. The work done is essentially force times a displacement, here given as delta y because this displacement is only in the y direction. So this is S. Work equals F times S. If our situation is such that the piston moves down and then returns to its original position, S is 0, so work becomes 0. That's not to say this engine has done absolutely no work during its motion. Half a cycle will essentially do work. We can say that the force is the pressure times the area inside this piston. That means work we can substitute into our work equation pressure times area in terms of force. So work becomes pressure times area times the displacement of delta y. A delta y is essentially going to become delta V, the change in volume. So work eventually for a piston like this, for any thermal engine we're looking at, becomes P delta V. Work is P delta V. And this is the principle on which most all heat engines actually operate. Here we have a diesel system in which diesel fuel is being compressed and it's causing it to combust. And here we are looking at a two-cycle gas engine. Here we have a spark plug which is actually providing a spark to cause combustion to force this fuel-air mix, this petroleum air mix to explode and force the piston down. It's still a heat engine, but it's one that requires spark. In the case of a diesel engine, it's the actual compression of the oil itself that causes it to essentially spontaneously combust without the need for an extra spark. And of course, basic steam engines operated on such a principle. Here we can see the hot air causing expansion and the contraction in the air in the cool air. This is a particularly clever steam engine as the air is being recycled, as the hot air is being taken by this little piston here and then allowed to move over here to give greater efficiency and actually give us an extra cycle here and actually cause an extra expansion, giving greater drive and more work being done for a single cycle. So that's the complexity of steam engines, was essentially the mechanisms attached to them to extract the energy. The actual principles on which they're based are those we're discussing here, which are not terribly complex. So in a model heat engine, here we have our high temperature, TH, at QH, and we're going to exhaust our energy, our thermal energy Q, to a low temperature reservoir. So here's QH coming out, being exhausted, QL to low temperature, and here's our work being extracted. But we cannot create energy. We cannot violate the principle of conservation of energy. So the energy that goes in essentially must be the energy that comes out. We are simply diverting it to do useful work. And the equations that dictate this are saying that Q hot or QH is equal to work plus QL, Q cold, or Q hot minus Q cold is equal to work by a simple rearrangement. So what goes in must come out. And this is actually exemplified in something referred to as the Carnot cycle. We'll discuss this in a little more detail shortly. But cast your mind back to when we talked about PV graphs. And here is a pressure volume graph, and here is a hot isotherm and a cold isotherm. So any point on this graph is at the same temperature, and any point on this graph is at the same temperature. We're merely varying pressure and volume. And as you can see, there's two areas of adiabatic nature, and then we have our hot and cold isotherms. We can actually denote points A, B, C, and D on this diagram. So we can talk about what happens from A to B, C to D, or D to A, or B to C. We can actually look at that in terms of this diagram. So here's the point that we're at in the cycle. Here we are in the adiabatic point. We're causing a compression. We're now at the top of our hot isotherm. Heat is going in. The system is expanding. Volume is increasing. Pressure is reducing. Now we're looking at an adiabatic expansion. Now we're looking at an increasing pressure, and a reducing volume. Adiabatic section, back to A, and now we're looking at heat flowing into the system, causing a reduction, an increase in volume, and of course a reduction in pressure. And that's how the Carnot cycle operates. We can actually extract work from specific parts of this, and we'll see that in a diagram shortly where I'll talk about where the work is truly extracted. You can probably surmise that from seeing what's going on here. So work is being extracted from the piston in two parts of this cycle. So in terms of our heat engines, here we're looking at the same diagram again. Here's our two isotherms, our hot and our cold isotherm in a PV diagram. There's our cycle. And essentially this is the Q hot, Q cold, energy available at the hot and cold parts. This is the cold temperature reservoir, the hot temperature. At this part of the cycle from A to B, we see an isothermal expansion with the temperature remaining the same. From B to C, we see adiabatic expansion. From C to D, we're looking at an isothermal expansion again, and at adiabatic compression when we're going from D to E. Sorry, this is compression here. And that's what gives us our efficiency equations. So we're going here from Q hot, essentially QH, to QL, or Q1 in this case, to Q2, same thing. If we're to look at the efficiency of our heat engine, then the maximum efficiency will be the maximum amount of work divided by the amount of heat energy available at the high end of the reservoir. This will equal 1 minus T low over T high, or the difference in the temperatures divided by the high temperature. So essentially, what is our gradient divided by what's the total temperature at the high end of our gradient. And these are the equations which really denote how efficient an engine is. So the efficiency of the heat engine is really the ratio of the work done to the heat input. How much heat have you got in the system and how much useful work can you get out of it? Or E is W over QH. And you can actually, as we said, use conservation of energy here for work and say QH minus QL. So we can say E is W over QH, or QH minus QL over what's the total energy available at the hot end here at QH. Or these are very similar to the previous equations, which are given in terms of T. These are given in terms of Q. The efficiency is 1 minus QL over QH, which is a simplification of this version of the formula. So let's take a look at an example. We have a steam power plant receiving 280 gigajoules, so that's 10 to the 9 joules per hour of power from a furnace. The heat is ejected at a rate of 145 gigajoules per hour, and because apparently they didn't insulate any of the pipes, there's an additional 8 gigajoules per hour loss through the pipes of the plant. Now we have two questions. Part A, how much work is done by the power plant? Part B, what is the efficiency of this power plant? So, how much work is done here? Well, work is essentially equal to Q. This is equal to, overall, 280 gigajoules per hour. So this is the work out. This is equal to the total energy budget. We've got 280 gigajoules per hour. We actually eject 145 gigajoules per hour, and we lose an additional 8. So we have to convert this. Here we have our value. So we've subtracted this off and we've got 127 gigajoules per hour. 280 minus 145 minus 86. This is 127 times 10 to the 9 joules. This is per hour. We want to put this in SI units, so we're going to divide by 3,600. This is 60 minutes times 60 seconds, which is essentially our per hour. This will give us 35.3 times 10 to the 6 watts, or 35.3 megawatts. Part B asked what is the efficiency of this plant? Well, we've just calculated W. We know that E is equal to W over Q. So substituting in, we have 127 times 10 to the 9 joules per hour, and we have a total Q of 280 times 10 to the 9 joules per hour. No need for a conversion here to seconds because the ratio should stay the same and the units should cancel, and that will give us a ratio of 0.45. As you can see, the efficiency is simply a ratio of the work to the heat. So we end up with a unitless value. We could alternately have used 1 minus QL over QH and stated that this would be 145 plus our 8 times 10 to the 9 here, which is essentially the loss, over 280 times 10 to the 9, and we would have ended up with 0.45. Either of these solutions would be equally valid. And this is really a matter of using the values you have at your disposal. A further example. Now we have a solar power plant with an efficiency of 0.03 and a net power output of 100 kilowatts. How much solar heat energy is going to actually be captured in the first place by these solar cells? Now, solar cells are incredibly inefficient things. So QH, how much solar energy in terms of heat, is going to be the work done over E. The power output was 100 times 10 to the 3 watts, and our efficiency is 0.03. This will give us 3.3 times 10 to the 6 watts. So a solar cell here is capturing 3.3 times 10 to the 6 watts of energy and only giving us 100 times 10 to the 3 useful watts. So let's take a look at some of these thermodynamic cycles and how these relate to a real engine, and then we'll segue into talking about how we can do the opposite of a heat engine and essentially have a refrigerator. So a Carnot engine, and you'll often see this particular terminology, a Carnot engine is essentially a 4-cycle heat engine. And we've already looked at these, but we didn't really call them Carnot cycles. And this is where we were looking at our isotherms at different pressures and volumes with our adiabatic expansions and compressions. And this is a system known as a Carnot engine. So the Carnot cycle, which was really put together by Nicholas Carnot in 1824, here seen in his younger days in his military uniform, was a thermodynamic cycle, and it really looks at how heat engines transfer energy from warm to cool and how much energy you can convert into mechanical work. And of course, how we can reverse such a cycle. So the Carnot cycle really looks at the heat engine as a PV diagram, as a pressure volume diagram with our hot and cold isotherms. We can then look at the expansions and compressions and which parts of the cycle we extract work from. And we already looked at that animated slide where we saw those different parts of the cycle. What I really want to do is show you exactly where work is done on the system or by the system, and that's what this part of the slide is really showing. So for a real heat engine here, we're going to lose heat to the environment. We're going to do what we said before, and we're going to exhaust our Q, our heat energy, to a cold reservoir and extract a certain amount of work. where do we actually extract that work? Well, we extract that on the part of the cycle where work is done by the gas. So here, along this hot isotherm, here we're looking at volume essentially increasing and pressure decreasing. So pressure here is going down. This is the point where our cycle gives us energy that we can convert into work. Heat is then extracted from the system from 3 to 4, so no work is being done here. And then we're doing work on the gas here. So essentially we're heating our system up again so that we can extract more work. So the total work done for this cycle, because the work done on the gas here should equal the work done by the gas, is 0. But we are getting work out of our system right here. And the efficiency, how much work we can get out of it, is governed by the equations that we used previously. E is W over QH, QH minus QL over QH, or E is 1 minus QL over QH, which of course you can always express in terms of temperature, as we saw in a previous slide. So the system can be worked on by an external force, and you can transfer thermal energy, of course, from our cooler system to a warmer one, and that's what those cycles were showing. And that can act as a heat pump rather than a heat engine. So that means we are, instead, as well as extracting useful work, moving heat from one place to another. The Carnot cycle is the most efficient cycle for converting thermal energy into work, or if we reverse it, using work to give us refrigeration. It's really a 4-cycle engine, and those cycles are actually detailed here, and you can see them in the PV diagram. This is merely an actual explanation of what's going on in the PV diagram blow by blow. So in cycle 1, essentially you're on the hot isotherm, and the expanding gas makes the piston work on the surroundings. We get useful work out of our system. The gas expansion is propelled by the absorption of heat from our high temperature reservoir. Cycle 2, the piston and cylinder are essentially thermally insulated, so we're not gaining or losing heat. The gas keeps expanding and working on the surroundings, and then the gas expansion causes it to cool down to going towards our cold temperature, Tc. In cycle 3, we're looking at a compression of the gas at the cold temperature, and then the surroundings do work on the gas, causing the heat to flow out of the gas to the low temperature reservoir. And then in cycle 4, the piston and cylinder being thermally insulated, of course, during that step, your surroundings do work on the gas, compressing it and causing T to rise to TH. The gas is then back at the beginning of the cycle. And this essentially is summarized here in our PV diagram with these particular annotations. So I would definitely, rather than memorizing those 4 slides, return to this and look at this and think about where is heat being added, where is it extracted, where is work done by the gas, where is work done on the gas. We're not completely free of steam engines in the modern age. We may not see them in the street or pulling carriages of passengers anymore, but we still do use steam in a very valuable capacity. So here we are actually looking at a generator which provides electricity, the kind of thing we're getting come out of the wall here, and this would be an industrial generator. And we actually do have a situation where we use either fossil fuels to release energy and create steam. That steam is then pushed through a series of pipes to higher pressure and turns a turbine, or we could use a nuclear system where we essentially just use nuclear reactions to heat water, create steam, and then push that water through a turbine. This turbine will turn, this will in turn spin a generator which will generate electricity. So we are still essentially using steam in a very important capacity. Here we're at TH, and then we're exhausting down to T low from the low pressure steam from the boiler. Now, as we mentioned during our discussion of the Carnot cycle, we can actually reverse our reaction. That means instead of moving heat in one direction so we can actually take heat out and get work out, we can actually reverse the reaction so we can pump heat from one location to another, therefore cooling one location. So as we said, back when we were talking about dropping our hot iron into cold water, heat will only flow down a gradient from a hot place to a cold place. When we did that with our engine, we flowed from hot to cold and we extracted work. What we can do in the case of something like a heat pump or an AC unit is reverse the situation and put work in and force air essentially to go from a cold reservoir, force our gas from cold to hot. So what we're saying is a reversal of the diagrams we saw previously. So here we're putting work in and we're forcing Q to go from cold to hot. So we're actually forcing cold air, essentially cold gas, to go into a hot reservoir. That requires us to put effort in, to put work in. You have to plug in your air conditioner, and then combined with a refrigerant and a fan pushing air over that refrigerant, you will end up with a cooling of the air and the air being introduced, cold air being introduced to a warm room. We cannot simply, of course, go from cold to hot. The second law of thermodynamics forbids energy from flowing this way, so we have to put work in to make this reaction possible. This will not happen spontaneously in nature. So heat pumps or refrigeration systems can be thought of a heat engine operating in reverse. And most common types of heat pump really work by using some kind of refrigerant. You need to remove energy, remove thermal energy from your system. And usually what happens is heat goes into expanding a gas, expanding a refrigerant. That refrigerant is then pumped away and the heat is allowed to dissipate into another reservoir. So if we take a common refrigerator such as this, here we have a motor and that's pushing the refrigerant through these lines. As it goes in here at low pressure through this expansion valve, it goes in at low pressure. The Q, the energy from inside the refrigerator, goes into expanding the refrigerant in these coils. That vapor from the refrigerant is then allowed into the motor here. That is pumped through and allowed into the pump that's powered by the motor. This is then pumped through this series of vanes and allowed to be exposed to the outside environment. This means energy is absorbed by the refrigerator as it runs through this part of the cycle, and then it's emitted by the refrigerant as it comes through here. So this is a specific chemical which expands readily and lets energy flow out of it quite readily. So energy is absorbed here by the refrigerant in this part of the cycle, and it's emitted from the refrigerant here as this part of the cycle. And that's what these metal plates, these vanes, help do in terms of allowing heat to radiate off. So here the refrigerant is under low pressure and absorbs energy. Here it's under high pressure and allows QH to vent to the outside. So we can take that whole complicated system that you can move your fridge from the wall carefully and have a look at behind your refrigerator. We can take that whole complicated system and we can look at it in terms of work and Q. So here now we put in work and QL goes into QH. So we take Q from our low temperature environment and exhaust it to a hot temperature environment. That means putting in work. And this is a typical kind of AC unit, you might see. So here we have a condenser and an evaporator, and what's essentially going on is the evaporator is taking energy from the air itself. It goes through the compressor, goes through the condenser, and then essentially warm air runs over the fan here, and this air is then cooled by the evaporator and then moved outside and lost by the condenser. This is why if you have a window unit in an air conditioner, it has to hang out of the window, because the fan is essentially providing cold air by running the air over the refrigerant and the evaporator and allowing the refrigerant to cool the air and forcing it to cool, and then running down through the condenser, dumping that heat outside, and then providing you with cold air. So in terms of refrigeration, you might recognize this formula, essentially one as this was efficiency before, Q and W, the ratio of these two. But this is referred to in terms of refrigerants as a coefficient of performance, or COPR, coefficient of performance for a refrigerant. And this is essentially the heat going in versus the work that you put in, where work in is defined as QL minus QH, or Q out minus Q in. So essentially a reversal of the formula we've seen before, because we're reversing our heat engine to have a refrigeration system. So let's take a look at one final example. Here we have a house to be cooled by an air conditioner with a COPR, a coefficient of performance of the refrigerant, of 2.5. The house contains 800 kilograms of air at an initial temperature Ti of 32 Celsius. The air in the house is to be cooled to 20 degrees Celsius in 15 minutes. Pretty impatient. So, using C for the air, this is the C value, the coefficient here of 0.72 kilojoules per kilogram Kelvin. So this is the specific heat of the air at 20 degrees Celsius. So we do need specific heat, and to harken back to a previous class. So how much heat is removed by the air conditioner, how much power is input, how much work is put in, and what rate is the heat ejected. So part A, how much heat is removed by the air conditioner? Well, we have here, we have a C value for the air here. We have a specific heat for the air. So Q is essentially equal to delta U, the change in energy. This is going to equal MC delta T from our previous calculations. Our delta T, of course, we have 20 to 32. Our T2, our final temperature though, is 20. So this is inverted compared to usual, and this is going to be 20 minus 32. We have mass, we have C. C here though is given in kilojoules, so this will have to be 0.72 times 10 to the 3 kilogram joules per kilogram Kelvin times delta T. This is going to equal then negative 6,912,000 joules. This is negative because heat is being removed from the air conditioner, and it's negative because this delta T value here will be negative and change the overall sign of this calculation. This means QL overall, how much heat is removed. The total amount of heat is just the modulus of this, 6,912 times 10 to the 3 joules. Part B, what was the power input to the compressor? Well, QL, first of all, is going to be 6,912 times 10 to the 3 joules. We know that energy, that's the energy we just calculated, but a power is an energy per unit time. So this 6,912 times 10 to the 3 joules over 15 minutes. We of course want to do this in SI units. So we take our 15 and multiply it by 60 seconds. So 15 by 60 gives us 900 seconds. So 6,912 times 10 to the 3 joules over 900 gives us 7,681 times 10 to the 3 watts, or 7,681 kilowatts. Part C asked us, overall, how much work are we going to put into the compressor to cool this house? So how much work is this thing going to do, and how much electricity is it going to use to cool my house down to 20 Celsius in 15 minutes? Well, quite simply, work is QL over COPR for a refrigerator. So remember, this is essentially the efficiency of our refrigerator, and this is the energy at the low end of our temperature spectrum. This is going to be 3 times 10 to the 3 joules, or more correctly, 3.07 thousand, 3.07 times 10 to the 3 joules. Part D, the final part now, and the end of this lecture. At what rate is heat ejected to the outside of the house? Well, the work put in is QH minus QL. We already know the work put in is 3.07 times 10 to the 3 joules from part C. This is equal to QH minus QL that we also know, what we also calculated, which is our 7.68 times 10 to the 3 joules. So QH will be 3.07 times 10 to the 3 plus 7.68 times 10 to the 3, which overall will give us 10,751 watts, or 10.8 kilowatts. And that really takes us to the end here, our conclusion in terms of discussion of thermodynamics.